Is that it? In some sense, right? A bit disappointed, a bit not. Okay, everybody. So I'm talking in my last lecture today. I have a lot of ground to cover. And the first thing that I want to do, so first of all, even though I'm not using my written notes anymore and projecting them in, on the fly, I am making them also available. After the class today, I'll just export this and put on a Google Drive, and I think the link to the Google Drive is somewhere on the website there, right? So all the notes for this class will be there, along with the slides that I provided initially, which have much more material and are based on my lectures. But today, I'm going to take a little bit of I'm going to use a different order than the ones in my notes here because I'm usually taking a bit longer to explain things here because I want to really answer all the questions that you have and so on. So I'll keep talking here about the CMB today and what you can get out of it. And let's just recall again this really important plot here, which was first done basically or thought about basically by George Gamow in the 1950s. And it tells you something about what the universe is today and what it must have been in the past and in the even more remote past. So we have all these phases of the universe here. And, this is now, today, right? This is the epoch of when you have radiation domination, and from here on is matter domination, right? And in between here, there's an important phase, which happens around here, right? So this is at a redshift of, so this is redshift of about 5,000, and this is a redshift of about 1,100, which is the decoupling of the radiation from the baryonic matter, because the temperature goes below basically something like 0.3 electron volts, and that's when the atoms become neutral, the universe becomes transparent, and that's the formation of the CMB, right? So this is the stuff that you have to remember. And the details of this were not known by George Gamow in the 1950s because he just didn't know how much radiation was out there. Nobody had ever detected the CMB. This was only detected in the 1970s, basically. And then in detail, much later, in the past 20 years or so, okay? But the important thing is that these are the epochs here. So by the time that the CMB formed, the universe was just being dominated by matter, but there was a large amount of radiation as well, okay? So it's a matter-dominated regime already, but there is still a lot of radiation because it was just the transition. They were equal, just, when the scale factor was about 5 times bigger than here. So it was very recent. So the CMB formed in a matter-dominated universe, but also with a big component of radiation. And this has some important consequences. And let's explore them here in a qualitative sense, and I'll give you some equations to play with later. So imagine now, so you remember that we drew a plot here of what the density should look like at some initial time here. So this is rho at t dec, okay? So this is the density around that time, and I'm exaggerating here the what's happening here, right? It's these small fluctuations of order 10 to the minus 4, 10 to the minus 5. Really small fluctuations. If I look closely at one of these regions here, okay, what I have is that this region has some kind of an overdensity here, right? It's denser than its environment on average. Of course, you will also have regions which are underdense. The counterpart of this, so this is rho of x in that small place. The counterpart of this in terms of the gravitational potential here is that in that very same spot there, you have a little bit of a well of the gravitational potential. So things are attracted to here, to this overdensity here, right? Right? So let's just look at this gravitational potential. You can really think about this, by the way, in terms of the Newtonian potential, okay? It's really a perturbation of the metric, of the Friedmann-Lemaitre-Robertson-Walker metric, but that perturbation turns out to be exactly what you associate with the Newtonian potential if you look, for instance, for the quasi-static approximation and the weak field limit. If anybody has done general relativity, that's what it is. Okay, so that's really the Newtonian potential here. So look at the Newtonian potential now, and let's see what's in there, and let's make a picture which is a bit complex, but I think you're going to understand here. So here's your Newtonian potential, and you see you have a lot of matter here. I'm just drawing the matter here as my yellow dots here, and it's like you have a cup here filled with a bit more matter than the environment here. However, so if you just look at the gravitational potential by itself, gravity wants to pull things in. So gravity by itself, without any other force involved, would want to bring things more and more towards this gravitational potential, increasing that overdensity, correct? Right? So right when you form the CMB and you release the system, because when they are tightly coupled with radiation, the radiation is kind of dominating, it doesn't let these structures form. When the CMB finally forms, or when around the time when it's forming here, what's happening is that in an overdense region, you don't only have an overdensity of matter, but you also have an overdensity of radiation. Right? You have more and hotter photons here than you have over there. Okay? So, more photons with more energy as well. Now, what does it do? Now, think about this as kind of a bag. Of course, you don't have really a bag because you don't have the walls of the bag here. But it's like you collected more matter and more radiation in a certain place. That's why this is an overdense region, right? But the radiation there, it is, of course, relativistic matter. You cannot contain it. Once the system is free to evolve, and it's, of course, free to evolve at all times here, during this time here, right? Whenever you make a region denser and you compact matter and radiation there because of gravity, the pressure of the radiation wants to, this pressure of the radiation wants to push this away. It's like a spring here. So gravity goes like this. Pressure of the radiation goes like that. What happens when you have two competing forces? Well, in the beginning, gravity starts to pull things in. Once it reaches a certain density, then the pressure of radiation wins. And remember, gravity is weak. The pressure of radiation is very strong. It's direct interactions, right? Basically, direct Compton scattering, Thomson scattering, and that pulls it back. The result of this are oscillations. So this is basically a fluid of matter plus radiation that experiments, that suffers oscillations. These are, in fact, the very definition of acoustic oscillations, because they are pressure oscillations. They are driven by a force and by pressure. Okay, so this is literally a fluid, and we will in fact, in this class here, at the end of this class, we will use the fluid equations to describe this fluid. Now, there are some subtleties here, of course, right? For instance, radiation interacts directly with baryonic matter, but it doesn't interact with dark matter. So there's a part of this which is not feeling the radiation pressure. Dark matter, for instance, starts to go down and down and down, and the potentials grow and grow and grow. However, baryonic matter, no, it suffers the influence of radiation. So whenever you compact that baryonic matter, initially by gravity, then it will tend to dissipate because of radiation. As long as you have enough radiation here, because of course, as time goes on, the radiation decays, and then that effect of the radiation pressure goes down. So this is a changing situation that can be quite complex, but qualitatively, I just told you what happens, and it's clear, right? Now, what is the basic property of this baryon photon fluid? The fact that it has a sound speed and you know what the sound speed is? I already discussed with you before. It's basically 1/3. This is 1/3 of c squared. In principle, if you had only a radiation fluid, the baryons, they actually introduce some drag to this fluid, so it has some inertia. I will kind of ignore this for a while here. So it's approximately this. You can think of this as just a radiation fluid. It doesn't matter too much. But you have the sound speed here, which is what determines to you what are the oscillations. So if you want to compute the angular frequency of the sound waves in this fluid, these are Cs times K, right? Which is Cs times 2 pi over lambda. Now, knowing this, let's see what happens when you have different types of structures experiencing these oscillations. Of course, you can look at this figure that I drew here, and you can decompose into Fourier modes, which is the best way of looking at this. And you have some small modes, K large, lambda small. You have some long wavelength modes, K small, lambda large, right? And you can decompose a fluid like this. And if we look at the at the amplitude, so I'm talking here about the amplitude. You can think about this in terms of the amplitude of the density, for instance, or you can think of this about in terms of the temperature of the fluid, the pressure, whatever you prefer. It doesn't matter too much because they all will be related to one another. Yes? Primordial black holes would be, at this time, would just work just like dark matter. They would not be interacting directly with photons. This cross-section for photon scattering by black holes, by primordial black holes, I mean, it depends on the model, but it's usually very, very small. So they don't interact, for all practical effects, they don't interact with the photon field. So they are like dark matter. Oh, that has nothing to do with any of this. For sure, this cannot happen. For sure, this process here doesn't enhance the formation of compact collapse objects because of radiation pressure. Of course, you can have collapse from dark matter, but you can have this from much earlier on even, right? So that process just driven by dark matter itself has nothing to do with what we're talking about here. We're talking here about this transition from matter to radiation and the interaction between baryons and photons. Dark matter is there in the background, okay? And it's doing its own thing, and it's contributing to that gravitational potential. But, you know, if you have some, let's say, exotic model with black holes and so on, then you have to treat it kind of separately. Yes? When you're talking about matter, generically, it is both dark matter and baryonic matter. They are both cold. They are both dust, okay? But baryonic matter does interact with photons. It doesn't matter that it's interacting with photons to its kinetic energy. Remember that we are talking here about photons which have a typical energy of electron volts. And the mass of the electron is 500,000 electron volts. So at most, when they get scatterings from photons, they get a 0.000001% of kinetic energy at most. So they're still very much non-relativistic. Therefore, dust. So even baryons are dust at this time. It's only if you really go to higher energies, to energies of, you know, many keV, MeV, mega electron volts, that really electrons become relativistic. And then you have to go to energies of GeV, such that protons are relativistic. After that, so this is much, much later than this. Okay? Yes? I'm sorry, you had several questions inside that one question. So, the generacy pressure? No. The densities here are tiny compared with the densities in places where this matters, which is like the sun or something like this, where well, not even the sun, you're talking about really compact stars. The densities here, remember, the density okay, so let's just make some numbers here so dark matter is approximately 5 to 6 times the density of baryons, first of all, okay? So they're not huge, they're a bit larger. Second thing is that rho 0, that's today, is about 10 to the minus 33 grams per centimeter cube, okay? So that's about a few protons per square meter. That's kind of ballpark where it is today. At the redshift of where we are talking about here, those scales, which is about 10 to the 3, you can make the calculation here. What is the density of matter, which is basically this, okay, of up to factors of order 1. So what is the density of matter at decoupling, right? Can you tell me immediately what this has to be? 10 to the 9, so that's 10 to the 3 cube times 10 to the minus 33. Okay? That's still very small. When you're talking about degeneracy pressures, you're talking about things which are, you know, 30 orders of magnitude larger than this. So forget it. All right? Now let's go back to the amplitude of these fluctuations here as a function of time. And let's say that this is the time when radiation decoupled from the baryons. And remember, when radiation decouples from the baryons here become transparent, and then the radiation kind of moves away. It is kind of homogenized, at least on small scales. And then these potentials here, they have the baryons and the dark matter, and they all are unaffected by the photons anymore. They are not affected by photons anymore. So now they can just grow and grow and go with these gravitational potentials. Okay, so these oscillations, they happen up to the point when there's decoupling. After that, there's no radiation pressure anymore, because matter is transparent. Radiation pressure is only effective when matter is ionized because of Thomson scattering. Is it clear? There's a lot that's a lot of stuff that I'm saying here without writing equations and so on, but the general picture is this. So I'll repeat. From the time that the universe becomes matter-dominated to the time where the radiation decouples from the matter. That's it. That's from when the universe becomes transparent. This process of acoustic oscillations with this sound speed is going on. At decoupling, very quickly, the universe becomes transparent, the photons decouple from the baryons, and these oscillations stop because now there's only gravity. There's no more radiation pressure. Is that clear? So let's look at what's happening with some regions. Let's say you have an overdense region here, and you have kind of this wavelength here. All right? So this is what's happening. And of course, this is pictorial, of course. So this lambda, right? And this omega is CS 2 pi over lambda, like I said. And you have also other scales. Let's say 1 over density here, which has a larger scale, goes like this, like that, like this, like that, and then it grows. Why it's growing here? Because of gravity alone. You don't have pressure anymore from radiation, so when you have an overdense region, it just starts to grow. By the way, this is slightly underdense, so I should say that this is probably going like this, right? Now, let's say that you have an overdense region here with a very long wavelength here, such that it experiences one oscillation only. So it gets here. So now this is the longest wavelength, so this is T of the largest wavelength mode that you can have, right? So basically, what we find is that here you have lambda max, which is going to be basically CS. So this, remember, this is 2 pi over this period here, right? So we have that lambda max is CS times this T max. Correct? Basically. And what is this T max here? Is basically the entire time that you spent from, let's say, redshift of, I don't know, 10,000, 50,000, doesn't matter too much, up to redshift of 1,000. So it's pretty much all the age of the universe up to that time. So really, T max, what it is that it's the integral of, it's basically dt from infinity, let's say, to z dec when this stops, right? Right? So this is basically it. So you can even write this as an integral dz, c dz over h of z from infinity to z dec. So that's your T max here. Therefore, there is a characteristic scale for these oscillations. For these acoustic oscillations. This scale is lambda max, which is basically, to be fair, this is basically the integral of c dz over, so basically c squared over cs of z. Remember, this is not exactly 1 over root 3 of z times h of z from infinity to z dec. And this is called the acoustic horizon. Now, this is really powerful, actually. So this is the maximum wavelength of an acoustic wave in the universe. So if you look at the CMB, you will see that scale imprinted on the CMB. It's in there. You can detect it, right? Because it's the wave corresponding to maximum compression at the initial time. And that has exactly one oscillation until decoupling. Right? So that's a characteristic scale that's in there. Now, we can both measure this on the CMB, and also because of this formula here, we can calculate this as well. All that we need is h of z, but h of z is just given by the Friedmann equation. So if you have a model for how much matter radiation you have to have, then you plug it in Friedmann's equation, and you have h of z from the Friedmann equation, from the first Friedmann equation. Now you have something that you can use to check for your model, and there are many things that you can get out of this. Is that clear here, what I've said so far? I made some simplifications, but the truth is about this. Okay, so this is about as close to the truth as possible in a class like this, at least. Yeah, it's because of baryon drag. It's because you don't really have a pure radiation fluid. You have this inertia. So whenever that radiation is hitting a free electron, because effectively that's what they're doing, it is not really carrying the free electron with the speed of light, it just drags. So the photon doesn't propagate freely, it still interacts with matter. There is a kind of an inertia to this fluid. It doesn't have zero mass. It's a fluid with non-zero mass because of the baryons. Basically, that's it. So the CS, I might be writing wrong here, but CS is equal to 1 over root of 3 times 1 of square root of 1 plus 3 rho baryon over 4 rho radiation. Something like this, okay? It might be 4 and 3, I don't recall. I think it's something like this. Right, so basically, if this is relatively small, then this is 1 over root 3, something like this. Okay? But you know, let me just put a question mark here because I'm not 100% sure of the numbers here. Don't recall right now. Yeah? What is written where? Measured. On the CMB. So we can both measure and calculate this scale. Now, more questions about this? Because you have an acoustic, you have a fluid from the very beginning you can think about, okay? Not from z equals to infinity, but it doesn't really matter. You can think z is equal to 10 to the 6, I don't know. And that fluid is going to compress and then expand. If this is a small wavelength fluctuation, it will compress and expand several times, right? But if it's a larger wavelength, it will take longer to compress and expand because, you know, the angular frequency is going to be proportional to the one of the wavelength, right? So the longer the wavelength, the longer it takes also, right? So there is one scale, which is a preferred scale, which has the maximum compression here, and here also, that took the longest to do this. So that's a characteristic scale of a fluctuation that was there in the beginning. So it's a wavelength. So it's a time, so the time gets translated into a wavelength because of the sound speed. The time it took was the entire age of the universe up to that point. And when that point comes, this thing is released and everybody starts to behave like basically like a power law. I will show you later. No, there will be the beginning. So, right. So during this epoch here, you were not really forming structures because the baryons couldn't really accumulate more and more and more and become a completely gravitationally collapsed, gravitationally bound structure like a star, a galaxy, or something like this, because the radiation pressure wasn't allowing it to do that. Okay? It's only after this point that you can have structure formation per se. It's after the decoupling. Okay? Okay, so good question that takes me into the next thing that I was going to say. So let's draw our picture here again. I'm here in the center, and I'm measuring something which is coming from really far away, from kind of a sphere around us, right? And if we draw those same fluctuations there on the sky, we're going to see stuff like this. Small fluctuation is like that, right, etc. A longer wavelength fluctuation will be like this. And the longest wave fluctuation is something like this. Correct? So these are the amplitudes here at this point. I'm just not making this mode radial, I'm making this across the line of sight. I'm making it curved, which of course doesn't make sense for Fourier mode, but if you think in harmonic space, that's pretty much the same thing. Okay? The harmonic, you can fix a radius and think about exactly the process that I told you about there, and think about these oscillations in harmonic space instead of Fourier space. That's the same thing, okay? So, now you can go with the CMB, you can look for these patterns of fluctuations of temperature in the cosmic microwave background, and you can look, okay, I see a maximum here and a maximum there. Of course, this is statistical, so this picture here isn't really like this. Is statistical pattern. You look at many, you decompose the whole field into modes, and then you look at the amplitude of those modes, and you find that there is one scale which has a preferred amplitude. It has a maximum, actually, which has a certain angle here. So you see in your observations, there is a preferred scale. And max here, of course, it's not that, that this is the largest angle that you see, of course. This is the angle, or the L, from the spherical harmonic decompensation for the strongest fluctuation that you have, which is this one here, which has the biggest peak here. The other ones, they are, you have many of them. You remember that you have many of these small wavelength fluctuations. They will all kind of cancel out. Their phases will just drop out, so they will tend to be smaller. So you can observe this angle, or this scale L. Remember, L here is from the YLM. When you decompose the map of the CMB into spherical harmonics like this. And that's the L, right? Because the M is really just, it depends on your choice of what is the Z-axis, and it doesn't really, so it doesn't really make any difference. It's just you average over the M. But the L is really a scale, right? That the L is independent of, you can rotate your system and the L's still don't mix. The M's will mix, but the L's will not. Yeah? Well, this is if you have just so you can imagine that this is your sounds. So this would be how you translate. Sorry, there's no C here. There's no C here. Because this is T. If I put a lambda here, then you would have a C here. And that's why you would have a C. So you can imagine that this is like this. So this is the correcting factor here for this sound speed there. Sorry, I'm mixing up things here. Sorry. It's sorry about this. It's really this. What am I doing here? Sorry about that. It's really this. Okay? I don't know. I'm not looking at my notes, of course, and sometimes I mixed up. So, of course, it's just CS there. Okay. Now, remember that, how do I, now recall our, maybe, I think it was the first lecture. So, I have some scale here, which is this lambda max, which is this, what I call the acoustic scale here. I don't measure this directly, but I measure this directly, right? This is right there in my observations. Doesn't depend on any choice. I can measure this directly from taking the CMB data. So how do I relate this theta? Let's call this theta S here, okay? Instead of theta max, theta S for. How do I relate this with RS? I'm exaggerating here the size of this angle, okay? It's about 1 degree in the sky in reality. So in radians, it's really small. So how can I relate this to a physical scale that I know has to be there? By the way, this theta S is about 1 degree, and this RS is what we call, in terms of megaparsecs, it's about 100 megaparsecs. Okay, so that's what comes out when you use the standard cosmological models here. So this is a very small scale. This is a very small angle. How do I relate both of them? Do you remember? What is the distance that we use when we relate a physical scale that we know across the line of sight in the angle direction with an angle? Well, it is a kind of radius, but remember, in Friedmann, Lemaitre, Robertson, Walker, there are many distances, right? There is chi, there's dl, there's dA. It's the angular diameter distance, guys. It's exactly the definition of the angular diameter distance. Remember that if you have some b and theta, and this is the distance here, dA, and then dA is b over theta. And that's the angular diameter distance, which is right? Now remember? Okay? So, the way that you relate these guys is this. So this theta here, we can write as RS over dA to Z DAC, okay? Where we can compute RS, like I told you before, is the integral between Z DAC and infinity. You have to change the limits of integration there. CS of Z dZ over H of Z, and dA to Z DAC is 1 over 1 plus Z DAC, 1 of square root of K sine square root of K times chi, where chi is integral between 0 and Z DAC of C dz over h of z. Now I put everything that we learned in this class together, right? Everything here we saw in this class, in these classes here, in these lectures, right? Everything. Except for this part which I just told you about today. Is that physical scale that comes from the acoustic scale, and the acoustic nature of this process is here in this C, this sound speed here, right? So let me know if there's any question about this, because this will come into your exam. Now, people looked up and like, okay, what? So ask me questions about this now, if you have any doubts about what I'm saying here. Yes?
Why does pi goes from 0 to Cx, but gamma goes from infinity?
Well, because you are measuring this distance here, right? Is the radius between us and that surface. Whereas this is an acoustic scale that has to do with everything that happened up to decoupling. Yes. So time of decoupling, so this is basically the integral from time is equal to 0 to the time of decoupling, and this is the integral between the time of decoupling and today. It doesn't really matter if you use instead of infinity, if you use 10 to the 5, 10 to the 6, or 10 to the 10, this integral won't change, because it's totally dominated by the lower end here. So it's very robust against where do you start computing. In principle, as early as you believe this process is going on as you predicted. So you can safely do this 10 to the 6, 10 to the 7. After that, you get a bit too close to Big Bang nucleosynthesis, and maybe you have to change things a little bit. But it doesn't really make a difference. Yes? Well, because I forgot to... Right? Thank you. And A is 1 over 1 plus Z. Okay? Anyway, so there are many things that you can do now with this. Jesus. I'm not being able to say anything. But anyway, it's okay. This was the most important thing. So this is perhaps the most important part, because also it's the most relevant part of what I'm saying here. So, two main pieces of information that we can derive from these relations. Okay? The first one is about spatial curvature. Notice that spatial curvature is appearing here. In practical terms, what this means is that we are over here observing a certain scale here, which I'm exaggerating, of course. This is your RS scale. And if we have, let's say, a flat space, then that dA there will be telling you that your geodesics, you can think about, this is just a representation, okay? Of course, these lines will all be straight no matter what, but the angle here will be this theta, let's say, for a flat space. However, if you have a space which is positively curved, remember what happens with a triangle in a space which is positively curved, right? If I draw a triangle, what happens with the vertices of the triangle? They get a little bit blown up. The sum of the angles of a triangle in a positively curved space are bigger than 180 80 degrees, right? So here is the same thing. This is what's happening to these null geodesics here, right? So what you see let's call this theta 0, is a larger angle. And vice versa. It's going to be hard to draw this now, but I'll try anyway. If you have a negatively curved space, then it's the other way around. You have this hyperboloid there, and you see an angle which is slightly smaller. Okay? Now what you have to do is that, well, let's assume I don't know much about the curvature of the universe, of the spatial curvature, but I know that there's a certain amount of matter or radiation and so on, and I can use this to constrain K. And the answer is that K is smaller than about 100 CH0 minus 2. Remember that K has dimensions of 1 over length square, and basically CH0 to the minus, square. Let me just be more, write this in a way that's this way. So the curvature radius of the universe is smaller than 100 times the size of the observable universe, which is this thing here. This is basically what we call the Hubble radius, which is basically commensurate, it's almost the same as the radius of your observable universe. It's basically 3,000 megaparsecs. So this curvature radius here is larger than 30 gigaparsecs, well, or 300. I don't recall exactly the number now. So it's an interesting fact that we can put a constraint which tells us that a certain scale is much larger than the size of the observable universe. And the reason for this is that even if it's a small scale, it still affects that angle in a very sensitive way. Okay? So it's an observable that carries information about a scale which can be much larger than the scale of the universe. It's kind of funny to think about this, but it's a consequence of the curvature which is everywhere. You see, we are not sensing the spatial curvature of the whole universe. We are sensing what is that spatial curvature doing in the patch where you live, where you make your observations. Is that clear? We're, of course, not measuring anything over the whole universe. There is no such thing, right? But we're measuring the effects of a certain constant of nature on our patch. All right? So that's one very nice piece of information. So the good thing about this is that we can forget about spatial curvature. It's negligible. So whenever we're talking about something like this, we really can just simply use, for instance, that dA is 1 over 1 plus z times chi. Much better, simpler. Huh? So that's one thing. Now, the other thing that this allows us to do is that the other piece of information that we can draw is similar to this, really. We can do more tests. So this is, let's say, the most robust and interesting one, and the one that we basically don't have anything else to rely on. That's the earlier, so this is so powerful because we are comparing a scale that we are very secure about, which is this acoustic scale, with a distance which is the largest distance that we can assess with photons. So basically, for all effects, it's the largest distance that we can observe anywhere. Before we see perhaps a background of neutrinos, but that's another matter. Probably never see it. But there are more tests you can do of the cosmological model. In particular, the Hubble parameter itself. So the way it happens now, it's a bit more involved because, you see, we observe this and we calculate these two things. And of course, you have the Hubble parameter both in this and in there. However, this is the Hubble parameter at an early time, and this is the Hubble parameter at a later time. But you can combine them and get constraints on the Hubble parameter in different times, right? So now, what's interesting about this is that this allows us to make a constraint on age from the time of decoupling to today, okay? And then if we use that constraint, we obtain a value of age 0, which is approximately 68 plus or minus 1 kilometers per second per megaparsec. Remember, 1 megaparsec is equal to 10 to the 6, sorry, 3,26 times 10 to the 6 light years. Okay, so that's the constraint that you have. So basically, this, you have to be sure that this is an extrapolation from z of about 1,000 to z equals to 0, okay? Because it's based on observations which are done with a field that's really living at redshift of 1,000, okay? So I know it's unclear how you do this, but you can imagine that having age here and there at different times, and you have to glue them up, and you have to combine them, then that gives you information. If you measure this, you are able to derive information about this. Okay? All right. Now, why is this important here? Because this brings me to the next issue here, which is, and I know that I haven't been clear about this, but just because it's just dirty now. You have to plug into a cosmological model here, you have to play with the constants there, with the parameters, and then you have to see what is the margin of the measurement of this. This is a measurement that you can do with less than 0.1% accuracy, and then you have to propagate to the other parameters that you have in these integrals. So it's dirty things, right? So, all right. Anyway, so why am I saying all of this? Because right now, cosmology is it's knee-deep into another crisis, yet another one, which is called the Hubble tension. Okay? I'll need to relieve myself of some. And basically, what is the Hubble tension here? So let's make our famous Hubble diagram here, which is velocity versus distance. In this case, it's the luminosity distance, okay? Well, in here, let's see how this plot is usually made. I don't want to make a plot which is different than the one that I'm using here for my notes. So let's just, which one I'm using here? No, it's the other way around. Distance. It doesn't matter too much, right? The luminosity distance and Z, or redshift. So several groups were measuring this luminosity distance from Cepheid stars, starting with Hubble almost 100 years ago, and this kept going on with better telescopes, with the better models, with better observations, and so on. But later, also with type 1a supernovas. And what they found with this technique here is that with Cepheids, you can start this after a certain distance. The Cepheids are just stars. They are like 10,000 times brighter than the sun. But if you get to distant galaxies, you don't see those stars anymore. Supernovas, on the other hand, are brighter than 1,000,000 or sometimes 1,000,000,000 times the sun. So you can see them much more far away. And they have this also same property that there is a relationship between the characteristic time of the explosion of the supernova and its luminosity. So people can use this also to measure the luminosity distance. Of course, this has some overlap here that allow people to calibrate this. And this is kind of what they measure here. Now, interestingly, a matter-dominated universe would have to behave like this. Remember that a matter-dominated universe is always expanding, but in a decelerated way. Of course, because matter wants to pull matter back in, so it decelerates all the time. Whereas this is telling us that this is really an accelerated expansion. Okay? So this is why we know that there is something like dark energy or a cosmological constant out there which is driving the acceleration. By the way, the error bars now are so small that it's basically impossible for this to be wrong. This is also verified by other observations that have nothing to do with supernovas, okay? So the fact that the universe is accelerating is beyond dispute. It's not relying on a single observation, but on many, okay? Now, the reason I'm talking about this here is not to talk about acceleration, it's because of something else. It's because if you use those observations of Cepheids and supernovas to draw what is the Hubble parameter, which is the slope of this curve here, you find that age 0 from these observations is approximately 72.5 plus or minus 1 kilometers per second per megaparsec. Now, these two are very different. In fact, you can think, let me make another plot here that makes this clearer. Which is cleaner here. So this is D, this is Z here. So basically, Cepheids per supernova are telling us that the universe is doing something like this. So they have a higher slope here. Whereas the CMB, it gives us a data point which is for very high redshifts. You can think about a data point over here, which is very safe. And it gives a lower slope. With an error bar which is uncomfortably small. So people have looked, of course, this result has been creeping up on us since a few years ago. And right now, nobody knows what's going on. People check this here, seems to be okay. People check this also, seems to be okay. The issue here is that we don't really see in the Cepheids and supernova the high redshifts. We only see up to redshift of 1 or so. On the other hand, the CMB doesn't really see this. We only have one data point here, and that's an extrapolation from high redshift. Now, of course, if you have something here that you're trying to match with something there, and they don't match, it might be that there's something wrong with our model inside here, or even around here. Maybe the data point moves because we don't understand exactly what the model is like there. And that's the situation as it is right now. Nobody knows how to solve this. And of course, who finds it out will be super famous immediately, will be super important, because this is a major embarrassment. So we don't know how fast the universe is expanding. It's as simple as this. There are two sets of observations. They are kind of similar, but they are within 4 to 5 sigma of each other. And that's it. We don't know what's going on. There's something there which is not exactly matching. It's close, but it's not exact. All right? Just one thing. I'm beyond my time already, and no, I know, but there was more that I wanted to say because I promised I was going to say, but effectively, there's no way that I can say this because I would need another 15 minutes or so. So it's up to the convener here to tell me, stop. It's in my lecture notes, you can see, but I promised to tell you how the fluctuations grow in the universe. Yeah. Okay. Is that okay? It's early in the morning. Unless you are in extreme hangover, you can still pay a bit more attention, right? All right, so let me just say a few words about structure formation, because actually it's in the title of these lectures, so I would be crazy if I didn't talk about that. So, a few words about structure formation now. All right, so let's go all the way to the front of my lectures here. Now, I'll go quickly over this, but it's really simple, all right? And you can look at both my written notes and my lecture notes. By the way, there are some factors in some of my lecture notes which are correct. So the idea here is that we look at these fluctuations in density here, right? And we look at what's happening with these overdense and underdense regions here. So we are not, and this is typically, I'm thinking here about in the matter-dominated universe. And after the formation of the CMB, the time of decoupling, okay? All right, so what we have to do here to consider deviations from perfect homogeneous isotropy is that we have to do stuff like this. Instead of having rho, the density to be some mean density, which is only a function of time, we have to make it a function of both time and the position also, which is, of course, approximately described by a mean density, but also with some small over densities here. So this is small. How small? Well, at the time of the CMB formation, this is like 10 to the minus 4. That's the number that we get from looking at the CMB. And the same thing for pressure, right? But remember, for matter or dust, the pressure is 0, so that simplifies things a lot. Also, the velocity here, instead of being just given by the Hubble flow times the physical distance, this is now corrected by some peculiar velocity. Let's call this delta V here, which is also a function of t and x. Of course, in order to have fluctuations, you need to be able to move matter around, so they have to have a velocity. If they didn't have any velocity, they would just stay exactly where they are and nothing would happen, right? Now, what happens, what do you have to use? What kinds of physical laws or equations you have to use when you are describing a fluid like this, right? What are the fluid equations that you have to use? Well, these fluid equations are just the set of fluid equations that you are familiar with. So basically, let's say, if you talk about energy conservation, you're talking about the continuity equation, d rho dt plus divergence of rho times v equals to 0. If you have momentum conservation, this is v dot plus divergence of gradient of p over rho, then is equal to some force, which is in this case our gravitational potential, right? And also, of course, gravity, which is basically the equation that tells you what is the gravitational potential in terms of the density here, the Poisson equation. So this is basically continuity equation. This is the Euler equation. And this is the Poisson equation. So I wrote this down as if I'm talking about Newtonian physics, but it turns out that if you perturb directly the Einstein equations with dust, you get these equations. Okay? Now, of course, we have to go into the trouble of actually implementing these fluctuations here, plugging them into these equations, all right? And there is some algebra to be done here. And I'll leave this as an exercise for you, which may or may not be asked in the exam. And turns out that it's very convenient to write these equations for this thing which I'm calling delta, which is a function of t and x, of course, which is delta rho of t and x divided by rho bar. So that's the relative density perturbation, okay? So basically the idea is that you start with the continuity Euler and Poisson equations, you perturb them with these small terms here. The zero-order perturbation theory are exactly the Friedman equation. The first order perturbations, when you write them in terms of this, and you combine the three of them, you will find a single equation for these deltas, which is the following. I don't recall the factor here. That's the equation for this density contrast. Okay? Now, interesting that I can combine them. Of course, the way that you do that is the same thing that you do sometimes in fluid mechanics. You take the gradient of this, and you take the time derivative of that, or sorry, you take the gradient of this. No, sorry, you take the time derivative of this and the gradient of that, then you combine them, and then you eliminate, because when you take the derivative of this, you get the Laplacian here, and then you combine all of them together, you get this. Okay, so I'll leave this as an exercise, but it's really simple. It's like 10 minutes, just open up, right? Now, it's super interesting that this equation turns up in a matter-dominated universe, because you see, there are no spatial derivatives here. No, it's not because it's isotropic. You see, this is a function of x. These are exactly deviations from homogeneity and isotropy. Okay? It's not because of isotropy per se, it's a property of matter. If you write these same equations for a matter and radiation fluid, then there will be spatial derivatives. But just for matter, there are none. Now, okay, now, this means that we can try some very simple solutions here, right? Let's try, no, besides, by the way, in the matter era, remember that T goes like, sorry, that the scale factor goes like T to the 2/3, which means that the Hubble parameter is really 2/3T, and we can use this in there and in there, right? So it's really, so the equation is really delta double dot plus 4/3T delta dot plus 2/3T delta is equal to 0. Sorry, minus here. Right? You guys can solve this like this, right? Oh, like this, come on. You remember, if you look at an equation like this, what do you think immediately? Well, these are two time derivatives. This is one time derivative, but there is 1/t here. This is, by the way, square here, I forgot. Yeah, sorry, there was a square here. I got excited here, trying to rush, not a good thing. So, and this doesn't have any time derivative, but there's 1/t square, which means that for every time derivative there is 1/t. There's always, so there's a 1/t going everywhere here. So what should we be looking for in a solution for this is a polynomial, it's a power law. So let's try ansatz, which is delta is proportional to something like T to the beta. Now, plug that in there, you have beta minus 1. So if you want to, let's say, a constant here, so constant beta minus 1, T to the minus beta, T to the beta minus 2. Then the second term will be 4/3 beta T to the beta minus 2. And the second term will be 2/3 T to the beta minus 2 as well. This is 0. This cancels out. This is an algebraic equation. Turns out that if you solve for this, beta will have two solutions. One is that beta is plus 2/3. And then the other solution is that this is minus 1. I think it's minus 1. Let's look at that. The important one is 2/3. The other one is unimportant. It's minus 1. So it means that if you look at this here, this means that mode grows. This is the decaying mode. So with time, of course, both are present in the initial conditions, but it's only the growing mode that is going to predominate. So now recall that what we have is that we have some initial condition. That delta at some initial time, let's say that the initial time is the time of decoupling everywhere. Putting these things together, this means that the density contrast at any time, anywhere, is just simply T over T DEC to the 2/3 time delta of T DEC X. And this is basically A over A DEC delta of T DEC X. So, bottom line here, the density contrast grows like the scale factor. Of course, this is true only in perturbation theory to first order. If you make an actual density field, some regions will be denser to start with. Even at the time of decoupling, there will be, you know, instead of being 10 to the minus 4, you'll find some regions which are 10 to the minus 2, 10 to the minus 3, whatever. And as things become denser, the process, which is initially a power law, then becomes exponential. So structure grows faster than this, but this is the basic point where you start. Now, the rest of this I'll just say, because otherwise I'm going too deep into the other lectures and so on. So, bottom line here, remember, some numbers here, just to finish this. So what is A at the time of decoupling? 10 to the minus 3. What is delta at the time of decoupling? Well, this really goes from 10 to the minus 2 to 10 to the minus 5, depending on whether you're looking at small scales or larger scales, okay? Typically, if you look at the typical scales, they will be 10 to the minus 4 or so, but there's some regions which will be this overdense. What it means is that you can only have a factor of delta of 1 today when the scale factor grew by a factor of 1,000. So you start with 10 to the minus 3, let's say. After an expansion of a factor of 1,000, not only the universe has expanded by a factor of 1,000, but your overdensity also grew by the same factor, such that today you can have an overdensity of 1. Is that clear? You start with something small, and you need to wait until it grows. Until that thing doesn't grow enough, you don't have planets, you don't have stars, you don't have galaxies. Bottom line here, the reason that we are here today after about 13.8 billion years of the age of the universe is that it took that long for the initial fluctuations to grow enough to form compact collapse regions such as planetary systems, stars, galaxies, and so on. If you look at the very early universe, there was nothing. There were no structures. It takes really a long evolution. It's not before a redshift of 10 or 5 that you really start to find galaxies. Of course, you find a few of them. If you look at the JWST data about, you know, super high redshift galaxies and so on, of course they exist because they are fluctuations of 1 chance in a billion, right? Of course, you will find something eventually because it's a Gaussian random field after all. But you find the universe totally dominated now by collapsed structures, you really need to wait at redshift of 1, 2, 1, or 0. That's how long it takes for the structures to grow. Okay? All right, so I should stop there now. Okay, sorry for going over time.
Last lecture, there's always something. So we have time for questions. We'll delay the next lecture a few minutes. So people have questions? So I had a question before they think of a question. So I would have thought that CS is not a, you say it's 1 over square root of 3 typically. Where does that come from? Doesn't it depend on the charge of the baryons and things like that? Or suppose the baryons didn't have charge. Like,
No, so CS of 1 over root of 3 is what you get from equipartition for a pure radiation fluid. The corrections for this come from the inertia of the baryons, the drag of the baryons. So it's just because of the Thomson scattering. So there is a interaction between the photons and the baryons because of Thomson scattering. But it's really the inertia. The Thomson scattering doesn't go into CS, right? It's just the fact that it exists, that is effective, that's going in there. It's the inertia of the baryons there. So the photons, think about this. There's a bunch of photons coming here, and you are an electron there, and we hit the electron. We give it a little bit of a momentum that way, right?
Yeah, but it depends on the electric
But the momentum
charge.
is more mediated by the mass, right?
Yeah, but why doesn't the electric charge come in at some point? Why doesn't it?
Well, it comes because of the only reason why they are interacting is because you have free electrons, because of the charge of the electron.
No, I understand, but then I would have thought that it wouldn't be just some number like 1 over square root of 3. It would have parameters in it.
Yeah, but there are. It was here, I forgot. So,
Those were the corrections.
so CS of Z is 1 over root of 3
No, but
times
that-
1 over root of 1 plus something like 3 or
but-
4 of rho baryon over rho radiation,
Okay.
right?
But suppose E was 0.
If E was,
like
if the
dark
charge
matter,
was 0,
like dark matter.
well, but then there will be no interactions and none of this will be happening. There will be no interactions. So the universe would be always transparent to start with, right? Because there will be no interactions between photons and matter. It's a charge interaction. You need the charge for the photon to
I
interact.
understand, but I just would have thought that CS depends on the amount of interaction, but you say it doesn't. The first term.
Well, you're correct. It should depend on the amount of interaction. So you're correct. It should be there. In some sense, it's subsummed, or it cancels, or it's effectively.
It must cancel somehow. Yeah.
Yeah, let's say that if you go to really low opacities or very high opacities, maybe there is a correction because of the Thomson scatter, which is the charge of the electron anyway, right? So it's a charge in the mass. But yeah, in principle, it should be there. I don't know. Maybe in some limit it is.
Okay.
Yeah, that's a good question. It should be there in some limit at least.
Other questions?
Here.
You talked about a neutrino background at some
Yeah.
point. What could we be seeing if we ever found?
Okay,
we
so
ever
if
could
we
measure
see, so neutrinos, I discussed this very briefly. They decoupled around the time of Big Bang nucleosynthesis, which is a redshift of 10 to the 10. So that's in the first 3 minutes of the universe, right? They decouple because that's the last time when they are interacting strongly via inverse beta decay, basically. So after that, they just stream freely, they propagate without hitting anything pretty much. So today they have a temperature of about 2 degrees Kelvin. So there's a background of neutrinos in the universe, which is really, really low energy, right? Now, if we can observe those, and it's really a long, long shot to observe them, then we would be seeing a surface which is a redshift of 10 to the 10. We would be seeing the same processes here, but now not in a fluid which is the same fluid that we have here, which is only basically protons, helium nuclei, electrons, and photons, pretty much. They will be much more complex than that, because we would have, the electrons at the time would be nearly relativistic, right? You would have not only electrons, but possibly the effect of electrons and positrons also, because the energy was so high that you could excite electrons and positrons out of any other particle just by the photons hitting any kind of a baryon or nucleon. So the type of the plasma would be different there. We would see something similar to what we have here, and I'm sure there are some papers out there about this, but it doesn't come to my mind immediately. But you will be observing something similar to this. However, Notice this, that the actual co-moving distance to a redshift of 1,000 is almost the same as the co-moving distance to a redshift of 10 to the 10. Because the universe was so smaller at that time anyway, that the extra redshift is really a small distance. So you would be seeing a little bit further into our past light cone, but not much more. Nevertheless, it is, yes, more information, but it's a really long shot. Neutrinos, even when they have, giga-electron volts, they are hard to find. When they have electron volts, 1 billion times more difficult. I don't know.
Thank you.
So how the influence of dark matter is taken into account on the structure formation?
Yeah, right. So, so this here is after the time of decoupling, right? So after the time of decoupling, there is effectively no difference between dark matter and baryonic matter because they're not interacting with radiation or radiation decoupled anyway and decayed faster. So at that time, it doesn't make any difference. Before the time of the decoupling, it does make a difference because when you have those gravitational potentials, dark matter falls there and keeps falling and keeps falling. It doesn't respond to radiation pressure like baryonic matter does. So you have to take that into account. And by the way, this means that there are several different coupled equations for this fluid. The baryons are interacting with the photons, and they are interacting with the dark matter through gravitation, but gravitation is not interacting with the baryons and directly with the baryons and the radiation through the pressure. So this is actually a simple but a complex system of equations that we can solve. But again, it's like I said, the only thing that you need to know to write those equations down before you solve them is general relativity and atomic physics, which is known for 80 years. It hasn't changed. Okay? You get a system of equations, which is quite long, actually. It's called the Einstein-Boltzmann equations, and you have to solve them. It's kind of something you have to do in a computer. You cannot solve them anymore by hand. But it's basically by, we have a certain amount of each one of them, you plug into your equations, and then you just propagate them in time.
Okay, so let's thank Raul for all his lectures.
Thanks, everybody.